confirm the form factors. Look, the form factors are generally given in your table. So if you are using universal beam or universal columns, is the form factors given. Let me check. Here you go. The form factor is given here. The value for the form factor is given to you in the one still tables. Okay, all the sections has a form factor. The form factor basically representing that whether your columns will have a buckling or not. If you have a form factor 1, meaning that your column will not going to buckle before it will yield. So this is fully effective. All this area when you load it is fully effective. That is Kf equal to 1. This is form factor 1. Basically it's saying that form factor 1, the form factor equal to 1, no buckling. That's what it says. There is no local buckling. Now if you have form factor less than 1, that is in the some of the cases where you have used the thin, you can see this is thick and this is thin. So in that case you will have these cross sections are effective. So this is effective, and let me put this way. So these are effective area, meaning that this will not buckle. That is effective area. And this one is ineffective area, meaning that this part will buckle. So we need to remove this part from our systems, right? Our systems mean in our calculation. So we need to remove that green part. So in that case, it will apply Kf less than 1. So that's what basically is saying. What is the equation for Kf? Kf equal to gross effective area over, and effective area is, by the way, this red one. So let me put this effective area over gross area. Now where are you going to get this one? The form factors. Now by the way, this is the we done the section number 5, the bending one that we finished. Now we need to talk about this why my camera is okay, let me put this way. Okay, so we're going to go through this section 6, which is the members subjected to the axial compressions. Look, it's very simple, only 2 or 3 or 4 kind of equation, maximum 5 equations that we're going to do, and they are very simple equations, not big equations. So clause 6.2.2 has a form factor, basically effective area of our gross area. If you have a compact sections or is thick wall sections, you will have gross area equal to effective area, your Kf equal to 1, and if it is Kf less than 1, then you have a buckling. So that's what the form factor. So basically the one still tables give you these form factors, but these examples want us to calculate the form factors and match it with the one still tables. So this is the grade 300, and it has given 610 UB101 and determining the section capacity NS. So the section capacity NS, by the way, is given here. Section capacity represented by NS. NS is equal to Kf, An, and Fy. So let me write it down. So in here, let's say section capacity of columns that is represented by NS equal to Kf, An, and Fy, and this one coming from clause 6.2.1. right? So we're going to find out this. Before we do that one, we need to confirm the value of Kf. Confirm Kf equal to how much? What was the sections given? Section is 610 UB101. So 610 UB101. So 610 UB universal beam. 610 UB101, and it has a Kf equal to 0.888. So Kf equal to 0.888. We need to check. We need to confirm that this value mathematically we need to confirm. So let's say Kf equal to AE over gross area, and that equation is basically coming from clause 6.2.2, and I will show it to you in a minute. That you have this clause 6.2.2 is a form factors gross area, effective area over gross area, effective area or gross area of the cross sections. So let's do the easy peasy job first. Easy peasy meaning let's get the gross area first. Gross area can be found, by the way, we are working in 610 UB101. So 610 UB101, and the gross area of the cross section, so 13,000 millimeter square. So let's put that value, 13,000 millimeter square. That is coming from one steel. That is coming from one steel, and let me put the reference as well. The reference is the table number 13. So that is coming from table number 13 of one steel table. Now that is good. Now we need to find the effective area. That is represented as a effective area. Now by looking at this one, by looking at this number 0.88, meaning that this 101 610 UB101, which is 610 UB101, may have this story that it may have buckling. So this part will going to be cancelled out. This part we don't want, but it is not always the case that you might have this is let's say flange, and this is wave. You may not, sometimes it may happen that your flange, sometimes it happens that your flange is fully effective, that the buckling does not happen, so which is good. And this only this part will buckle. These parts need to be cancelled. Only wave buckle, only wave buckles. We don't know, we need to check. Or it may happen that your wave is fully effective, but your flange might have this buckling, right? Your flange will goes off, right? So we need to check who is giving up first and who is taking part. So we need to divide this one into two sections. Meaning once we're going to check flange, there is no any rules. You can check the wave first, or you can check the flange first. So there is no any rules. We can check one interchangeably. So there is no any hard and flange rule. So let's start with flange one. So let's check the flange, whether it's gonna buckle or not. Now the standards has like the equations whether it will buckle or not. So standards is telling me, let me open the standards for you. Now standards has, look, this standards has these equations, which is the here clause 6.2.3. it has given the plate elements analysis. Again, the columns, we will not going to work against the whole column. We're going to divide the whole columns into the plates. Plates meaning that flange is the one plate and wave is the one plate. So lambda E equal to B on T square root Fy on 250, which is the plate element slenderness represented by lambda, like in the beam. So we get these equations, we're going to calculate B, we calculate T, and for circular hollow sections, we no need to worry, we just want to worry about this flat plate. So we're going to calculate lambda E, and we compare against our yield slenderness length. If lambda E is less than lambda EY, it is fully effective. So let me put in the context. So we have lambda E is equal to B on T square root Fy on 250. By the way, that is coming from clause 6.2.3, and we will check meaning lambda E is, let's say, less than lambda EY, then you have no flange buckling, right? Meaning we don't need to calculate the B effective. And if lambda E greater than lambda EY, we say that flange buckling occurs. So there is two conditions, okay? Condition occurs. So by the way, it's telling me this one, that you have your columns made of flange which is that thick, just represented. This is the thick flange. There is, let's say, thick flange, and it will not buckle. Thick flange. And let's say if you are using this flange, then it will buckle. It will buckle mean it will does this. By the way, this buckling meaning it will does this, that this part will goes like this part will goes like this, and this will stay straight because it's supported, and it does this. And so therefore we want to remove this part, and this part will does this, and this part will does, if it is thin wall. And this one here, it will does this. By the way, this will stay straight, and then it does this, that straight like this. Okay, so that's what happens in the web. So we need to remove that part. So depending, the standards is telling me whether, so by looking you don't know whether it will be going to buckle or not. So then the standards wants you to check these conditions, that your element slenderness less than yield slenderness limit or not. Okay, so that's quick checks will help. So let's say lambda E equal to the B value. In our case, B value is basically for flange is this one. From this part to this part is B, and this part to this part is T. So let's grab the T first. Thickness of the flange is 14.8. So let's put 14.8 here. 14.8. What is this width? Thickness of the width. Width of the flange is 228. That's fine. Let's put 228. And this thickness is thickness 10.6. So that is 10.6. So if I want to calculate this B first, let me calculate this B first. B for the flange. Let's say B for flange. This B can be found by taking this 228 divided by 2, take away this 10.6 divided by 2. So if I do the quick calculations, 228 divided by 2, take away 10.6 divided by 2, you get 108.7 millimeters. Right, does the one steel tables give us that B? No, straight away they give you this B on T. We will check it. Now if I want to calculate B on T for flange, so you have 108.7 millimeter over thickness is 14.8 millimeters. So you get 14.8 millimeters, you get 7.34. Let's check it out. Let's check it out, meaning, yep, here, come on, here you go. That B on T, basically this is B on T for flange. This is B on T for flange, and it's 7.34. Yes, it is 7.34. So that is good. So then you can calculate lambda E equal to B on T square root 250. Square root Fy on 250. Square root Fy on 250. By the way, again, let me write the close is 6.2.3. Right, so let's put that in this one, 7.34, and yield strength of the flange. Come back here. Yield strength of the flange is 300. So yield strength of the flange is 300 over 250. So we just put in the calculator. Let's say 300 over 250 times by 7.34. It gives you 8.04. Now let's check. Check meaning whether buckling will occur in the flange or not. So lambda E, which is 8.04, and let's calculate lambda EY, which is yield slenderness limit. Now to get the yield slenderness limit, we need to use this table 6.2.4, which has a yield slenderness limit. We have a flat region. We have a flat plates. therefore we flat. We have a circular hollow sections, we're not using it, and longitudinal edge is supported, one edge is supported, outstand, and both edges supported. So what is one edge supported and what is two edge supported? So you can see these examples again that I use in the beam. Forget about this gray color one, and don't worry about that. Let's don't worry about that. Just say that this is a columns, and I apply this load here. I squash it. This part may buckle, so we might, if it is thin wall, we might go off. These portions will going to buckle as well. This part would be effective. This part would be effective. Now in that case, it's standard saying that if you have a flange, then your one edge of the flange is longitudinally supported. Yes, it is longitudinally supported by this wave. So in here, longitudinal edge is supported one. Yes, so this edge, there are two longitudinal edge in the flange. One edge is here and the second edge is here. Now this longitudinal one edge is supported, one edge is not supported. So we are basically talking about this one for flange. So basically this is flange and this is wave. In the wave, both longitudinal edge are supported. As you can see, when I load this one, this edge is not supported. So in here, we're going to work for the flange in this particular first line. Okay, particularly first lines, meaning that look, these numbers, I need to physically explain you what is this number, this 16, 16, 15, 14, and look at these numbers here. Don't worry about this circular one, but you can see the significant difference: 16, 15, 15, 14, and 14, 45, 40, and this one. So basically it says that we look, this numbers is telling me that this smaller number, that they will buckle, they are more prone to buckling. You can see that you need the your beam might this element will buckle first. So that's what these numbers physically means. Now here they have a different classifications. For all our one steel sections are hot roll sections. I explain you this hot roll and cold roll process. So there are hot roll process, so it's represented by HR. For that case, we have 16 as a lambda EY. So let's put that 16 lambda EY equal to 16. What would be the relationship? Relationship would be less, meaning that what does it means? Means flange will not buckle. Flange will not buckle, meaning that we have effective weight equal to B. So in that case, the flange will not have any buckling problems. Flange will just going to stay as it is. There is no any flange buckling occurs in this one. So flange is fully effective. It means that flange will not have any issue of buckling. So this flange will fully effective, and this flange will fully effective, right? So there is no buckling, so it's fully effective flange. Now for the case of wave, let's check the wave. Now wave, again we're going to calculate lambda E. Again we calculate lambda EY, and we're going to compare whether lambda E equal less than lambda EY, no buckling. And if lambda E greater than lambda EY, buckling occurs. Then calculate BE, effective weight. Right? So that's the quick check that we're going to make. We will do B on T square root Fy on 250, and then we will get this lambda EY from table number 6.2.4. So let's do one by one. Let's calculate lambda E first, which is B on T square root Fy on 250. Again, let me write the close 6.2.3, and let me show it to you in the standards as well again. So these equations can be used for flange, and this equation can also be used for wave. So there is no any hard line for that. Now that lambda E B on T, so in that case, if I redraw these sections again, all right, so this is the wave, and that is the B, and that is T. Now we can go back to this one steel table, table number 13, and we can get this B value for web. That is your D1, which is 572. Basically this D1 is 572, so I can write this is 572 millimeters. And the thickness of the web, let me close this, thickness of the web is here 10.6. so thickness of the web is 10.6 millimeters. Fy value, if you like, you can use this flange one 320, or you can use 300 given in the example is grade 300. They will not going to make a big difference. They just use let me check if it's not going to, yeah, they will not going to make big difference. Let's use 320. So let's calculate B first. B equal to 572 millimeters. Thickness is equal to 10.6 millimeters. B on T equal to 572 millimeters over 10.6 millimeters. Then you will get, let me calculate that, 572 over 10.6, you get 54, or you can say 50. Let me check with this one. There you go, 54 D1 on TW. So it's checking completed, 54, and lambda E equal to this 54 times by square root, let's put 320 over 250, then you have a square root 320 over 250 times by 54, you get 61. And let's take the lambda EY value. Now again in the tables, here both longitudinal edge are supported, flat longitudinals, hot roll, we have 45. So you have 45. So your lambda E, which is 61, is greater than lambda EY, which is 45. So then you have local buckling occurs in web. What does it mean? That if I load this beam under universe under compression, if I compress it, this beam will just going to have, this edge will not, they will just going to come out. So these portions in the middle part will going to come out. These middle portions will going to do this. This middle portion, this will the straight line, and then it will come out, and then it will go straight line, this one. So standards will gonna tell us how much your materials can be removed, because you can't use these materials. It will not going to carry the axial load. So this web is not fully effective. It has buckle, right? So in that case, the standards will gonna tell us. So now how the standards gonna tell us? That you can calculate BE, which is effective width, and that BE is given here. BE equal to B, lambda EY on lambda E, check, less than or equal to B. So that is close 6.2.4. So that is B lambda EY on lambda E, and then we need to check that BE is less than or equal to B. All right, so that's fine. B value is given to us is 572 millimeters. So let's plug that, 572 millimeters times by lambda EY is 61 over lambda EY is 45 over lambda E is equal to 61. So 572 times 45 divided by 61, you get 422 millimeters, which is less than or equal to B. B is 572 millimeters. So therefore it is okay. This check is okay. Now basically it says that your, let's draw this beam that is under axial compressions. Basically it says that you have this width which is how much? 572 millimeters. Now you can't use 572 millimeters because your this middle part is gone. This one is gone. Basically it just says that okay, this is, let's say, BE1 and this is BE2, BE2 and BE equal to, let's say, BE1 plus BE2. Standards is gonna straight away give you this BE. Right, so if I want to calculate the effective area, because this is this green one, let's say, effective area, right? So if I want to calculate the effective area, which is green one, equal to gross area, take away this ineffective area. Let me put the green. So that is effective area, and this one is ineffective area. So green one is gross area. Take away. Basically gross area is not green one, but effective area is the green one. So effective area is the gross area. Take away this ineffective area. Let's put the ineffective area. So in that case, gross area we can just get it from here, 13,000 millimeter square. 13,000 millimeter square minus ineffective area. We can just calculate that ineffective area here. Ineffective area would be this D1, which is 572. Take away this 422. Take away this 422 times by this thickness. Times by this thickness was 10.6. Thickness 10.6. So we have 572, take away 422 times by 10.6, you get 1590 millimeter square. So you have 1590 millimeter square, you get 13,000, take away 1590, you get 11,410 millimeter square. So that is your effective area. Now, if I want to calculate KF, effective area over gross area, 11,410 millimeter square over gross area is 13,000 millimeter square. That is your form factors. Where is that coming from? That is coming from your standards, clause 6.2.2, effective area over gross area. So if I just plug that one, 11410 divide by 13,000, you can get about 0.88. Right, so 878, yeah, almost there. So there is check here that you have almost with our value, form factor is confirmed, right? Because if you look at that one still tables on the next page, you have form factors given to us, which is 0.888, and that's how we calculate it as well. Now once you calculate the form factors, KF, we can calculate the section capacity. Right, the section capacity is represented by NS, KF, AN, and FY. KF is 0008. Look, this is your always gross area. Don't take, because you have two area. Either you can take effective area, gross area, but we already take into account by KF effective area. So you always take this one as a gross area, which is your 13,000 millimeter square, and this would be your minimum value, because you have two value, minimum of 300 and 320 because this is for flange and that one for web. So in that case, you can just take it 300 Newton per millimeter square. So the answer would be you get 0.888 times 13,000 times 300. You get 3463 200 newtons, and then you get 3463.2 kilonewtons. So that is your NS section capacity. If someone asks you to calculate with the capacity reduction factors, you can multiply by 0.9, 3463.2 kilonewtons times by 0.9, you get 3117 kilonewtons. And where this 0.9 coming from? That is our reduction factors. Reduction factors come from these. Here you go. Member subjected to bending, member subjected to the axial compression, section capacity. You have 0.9 coming from table 3. So that's the quick examples. I hope you understand this section capacity. Quite simple. We confirm the form factor first. I can show you how you can check the flange and web, whether it's fully effective or not fully effective. If it is fully effective, you don't need to worry. If it is fully effective, no need to worry about no buckling. If it's buckling, you need to calculate the BE and then effective area. And then you can check the form factors. Now that is a quick example for that one. Now the second examples that we like to go for it is to determining the design capacity, which is 5N for a concentrically loaded, concentric meaning axially, okay, axially loaded is the same word, axially loaded, and under compressions we have grade 300, 200 UC 52, 200 universal column 52, and it has a 3500 millimeter long. So if I just take the columns, you have these, assume that this is a columns and this is 3.5 millimeters, not by scales, but you can say this is 3.5 millimeter axially loaded, meaning it is just loaded. Like, you can't just apply the axial load, by the way. It's axially loaded meaning result means just you have a point here. It is just a whole, you have a plate here, you put the plates like a strong plates. How can I show you? Here you can have like a strong plates, and you can just push it with the strong plate, fix it here. So that's how they do the test in the lab. They can't just have this, they can't just have a point load here and they will apply axial loading, means the whole cross section just goes down. So that is the 3.5 millimeters about the x-axis and about y-axis. So both are same. So they have given. Now look, standards. Look, there are two kind of columns, that you have a short columns, or you have a long columns, Sometimes some book use slender columns as well. You can use this word slender columns. Now short columns only fail generally by local buckling. This will fail by local buckling, but this one lose the stability and it will fail by global buckling, meaning that your columns will do this. Your columns, let's say this is straight columns, and it will does this one. So that is you will have this lateral deflection, that is a global buckling when you have long columns, and here you have only local buckling. And in the long columns you will have a mix of local buckling and global buckling, because you will also locally buckle and you will have global buckling as well in the long column. Meaning that if I take this one, and if I have a strong column, if I have short columns by, let's say, tiny bit of columns, then you have only local buckling. Local meaning that this will deform this portion. Look, this part will not deform. By the way, in any given condition, T portions here up to this portion, they will not going to buckle. Only this portion will buckle, and this portion, this middle part will buckle. So this is local buckling. And sometimes if it is long columns and there is no any restraint, this will buckle like this. like in the beam. Do you remember there was a lateral torsional buckling? When there is a member buckling will couple, magical equation was come into pictures, and you have this lateral torsional buckling, not the sections. The same here, you have this global buckling. Global buckling means it will does this. I don't have no, I don't have that form. So it will just how can I show you? Yeah, so let me show you with this pen. So this pen will just going to do this global buckling, not the local buckling. So if it is long. Now, someone might say, Vipul, how do I know is it long or short? Well, good questions. The standards will gonna tell us whether it's your column is long or short. Okay, I will show you the tables. The standards will gonna tell us whether you have a long column or short column. Now, always we need to calculate the section capacity. We can't just avoid these always step one, you need to calculate the section capacity. Now, I already show you the detailed way if you want to check how to calculate the section capacity, but straight away I just calculate here kf, an, and fy. Now in here we have given the cross section, which is 200 UC, 52 columns. That is our given cross sections. So let me get the form factor first. If you come back here, 200 UC 52.2. So this, let me change to here 52.2. 52.2. In that one we have a form factor of 1, so meaning that there is no local buckling. So form factor is equal to 1. Gross area, by the way, this is always gross area, no effective area. 200 UC 52.2, and the gross area is given is 6660. So you have 6660 millimeter square, and the yield strength probably 300. So you have 300, 320, take it minimum. So times by 300 Newton per millimeter square, which is megapascals. So if you just use the calculators and do the quick calculations, 6660 times by 300, you get 199800 newtons, meaning that you have 1998 kilonewtons. If it is short columns, you can stop here. Stop here. If it is stop. If it is short columns, but standards will gonna tell us whether you have a short or long columns. How it's gonna tell us, I will tell you. All right, now we can calculate these few things here because we need to calculate this member moment capacity. I can show it to you here, because short columns, if you have a short columns, you have these up to here, like close 6.2 is for nominal section capacity, meaning short columns. You have a short columns 6.2 and you stop. But if you have a long columns, which is the global buckling and local buckling occur, 6.3 we need to take into account. Now then you need to calculate this effective length and Ke, and then you need to calculate this lambda n, and from that lambda n you need to calculate alpha b, and then you need to calculate alpha c. So there are quite few. One, and because you need to calculate this alpha c, by the way, nc is less equal to alpha c. This nc is member moment capacity, sorry, member axial capacity. So this is the if you want to calculate member, what happens there, let me check. Yep, you are not going to like it. Okay, member axial capacity, that is represented by nc, sorry, that is coming from here, nc, and alpha c, ns, and we know alpha c is called member slenderness reductions. Member slenderness reduction, and that is coming from table 6.3.3c. that is coming from these tables, table 6.6.3c, and that's tables require lambda n value, and that's also tables require alpha b value. So that's good. So we need to calculate for that alpha c. Before we calculate alpha c, we need to calculate lambda n, and we need to calculate alpha b because we need to use that. So lambda n is called, I think, lambda is, I think, the slenderness of the member. So let's say lambda n, and I will show you L effective over R square root kf fy on 250. This one coming from here, by the way. This one here, lambda n Le over R kf L fy on 250. Now, standards is not telling us whether you do the x-axis or y-axis, because we need to do the two process, because the columns can be buckled about the x-axis and column can be buckled about the y-axis, but we need to make a decision which one is the weak axis, right? By looking we can't say, we need to know the numbers. So x-axis and y-axis. Now the example says that length about x-axis is 3500 millimeters and length about y-axis is 3500 millimeters. Effective length is given, that not effective length, the actual length. So the actual length is given to us with 3500. That is your actual length. Let's say Lx only. Actual length Lx and actual length is Ly. Now that is given in our examples. Now if I want to calculate the effective length about x-axis, then we need to calculate Ke Lx, and effective length about y-axis I can calculate Ke Ly. Now what is Ke? Now Ke, does it says which boundary conditions we have? Column pin-ended. It is given here, pin-ended. So if you go back to, I think you just need to refer back all the way to the figure 4.6.3.2. Basically is structure analysis chapters. You know, structure analysis, when you do this Euler's buckling, you remember there was a boundary conditions, and there was a one figures here in this chapter. Look at these chapters. You have a brace columns and swim members. We always work with these brace columns for our course here, so don't worry about this one. We are on the brace members, and in the brace members, if you have a pin conditions, this is pin by the way, this is your fix and pin, and this is your fix. So that is shown here if you with the symbol. So here we have pin, so our Ke value, which is Ke is, they call it member effective length factors. It is called member effective length factor, Ke. So that is equal to 1 from figure 4.6.3.2. So Ke, and they are both on the same. They both Ke equal to about x-axis and about y-axis, because the boundary conditions will be applied both on the same direction. So if I want to calculate effective length in the x-axis, I would have same effective length. So effective length is not changing, right? So that is good. There is no any issue for us. And 3500 millimeters. So you have 3500 millimeters. Now, a second philosophy we need to get is the radius of gyrations. So the radius of gyration Rx about the x-axis. So let me go back in here. Radius of gyration about x-axis 88.2 and 51. So 88.2 millimeters and 51 millimeters, right? That is your radius of gyrations. Radius of gyration 51. Oh, by the way, this was 51.5 and 89.1. Sorry, I look at that wrong one. 89.1, 89.1 millimeters and 51.5 millimeters. Now, then we can take this ratio, effective length About x-axis, the ratio, this is called slenderness ratio, by the way, which is 3500 millimeters over 89.1 millimeters. It gives us the value is 3500 over 89.1, you get 39, and effective length about y-axis ry 3500 millimeters over 51.5 millimeters. So 3500 over 51.5, you get 68. 68. Now look at these two numbers. Now what is these two numbers is telling me? Now this is very important, please. Very important, meaning that it will gonna tell me whether my columns will buckle on about the x-axis or my columns will going to buckle about the y-axis. So basically, if I draw the column, sorry about this, my arts. If I draw about x-axis, then it will have a L over Lx over Rx value is 39. And if I do about y-axis, your Ly over Ry equal to 68. So which one is the weak axis? Where if I load it here, then which side it will gonna buckle first? Which side it gonna buckle first? Let me grab that one. That you have remember that 39 and 68 about x-axis 39. So you have about x-axis L over R ratio 39. So you will not have buckling about x-axis. So this will not gonna buckle about like this. It will not buckle like this. About x-axis, it will not going to do this one. But about y-axis, about this y-axis, you have what was the numbers? About y-axis 68. So basically, our weak axis is y-axis. So your buckling will going to occur like this. Right? I hope you understand that. So if you, I think I don't have a ruler, but if you have a ruler, I think in tomorrow workshop I will make sure I will have a ruler, so I explain you that philosophy. So basically you understand that, okay, where is the weak axis? So L over R ratio, slenderness ratio, larger the slenderness ratio, this is the weak axis. Okay, so it is a very critical that you have a larger slenderness ratio will give you the way which side weak axis. So you have this larger slenderness ratio about y-axis. So our columns govern buckling will occur about the y-axis, and basically it also go on because if you have same length, it will also go on by these smallest radius of gyrations. If you have same length, then if this one lower, then your slenderness ratio would be higher. So buckling, global buckling occurs about y-axis before x-axis. Yeah, it will occur about x-axis as well. I'm not saying it will not occur, but which one going to occur first? It will occur y. Why? Because your Ley over Ry, which is 68, slenderness ratio is greater than Lex on Rx, right? And that is 39. So therefore, this y axis is weak axis. So you can say y axis is weak axis. Okay, x axis is strong axis. You can interpret that one as well. You can also interpret that for same length, the smallest radius of gyration is Ry 51.5 millimeters. So y is weak axis, right? That is also you can interpret. There are many ways you can interpret that one. Okay, so that is the quick one that you need to check for global axis which one is the weak axis, and that is the quick check that you can make it. Once you find the quick axis, look, standards is very silent on that one. Standard is very silent on that one, meaning that I can show it to you here on these sections. I'm running out of time, but it's very important here to highlight. Look, standard is very silent, saying that he does not put LEX or LEY. They want you to figure it out which side your buckling will going to occur. It's not saying LEX, which LEX or LEY. So now our calculation would be based on YY axis. We're not going to work on X axis. So that's interpretation is very important. So lambda n now equal to LE over R square root KF square root FY on 250. So LEY is 68, not 39, please. KF is 1, we previously calculated. 300 on 250. You will get 74.4 as a slenderness factor. Now this lambda n, if we calculate it, we can calculate alpha b, and alpha b is called member section constant. Member section constant. Now that member section constant is given here. There are two tables to calculate the member section constant, table 6.3.3a and table 6.3.3b, depending on your KF value. Because in our section KF equal to 1, so we're going to use these tables, not these tables. If you have KF less than 1, you can use this table. So simple, between these two tables only you can calculate alpha b, which is member section constant. And in here we have a hot roll, universal beam and universal column section. So you have UC sections. So we take alpha b equal to 0. So alpha b equal to 0 coming from table 6.3.3a, KF equal to 1. Now once you have alpha b and lambda n, you can calculate alpha c, which is your member slenderness reduction factor. Now this is very important tables. Very important tables meaning that will going to tell me whether my column is short or long. Now look, lambda n value we have 74.4. But by the way, but before going on to this one, let me tell you something. Look at the number 1. Look at the number 1, meaning this is short columns. 1, 1, 1. There was no global buckling occurs. 1 meaning there is no local global buckling occurs. Look, 1, 1, 1 meaning short columns. Short columns meaning is short columns, like a short column, right? But immediately when is less than 1, your columns will have instability. Instability means it will going to buckle. It will go into global buckling. So here no global buckling, no global buckling, only local buckling occur if the KF is less than 1. No global buckling, no global buckling, no global buckling. Immediately this value is going to tell me. So by looking it's not going to tell you, but this table is going to tell me, very magical tables that going to tell me people it's going to do this one or not going to happen. So this is very magical table. Now we're going to identify whether our columns is short or long by putting 74.4. So we guess, look, these new standards, I don't like it. They break these tables into 2 pages. In the old standards, we have a very nice only on 1 page, but that's how they decided, by the way. So you have a 74.4, so almost 75. You can do interpolations between if you have intermediate value, and alpha b value 0. We just got it. 75, you have 0.715. Almost 30% penalty has given to you on the columns because you have a global buckling, because you have a long column, 3.5 meter columns. Okay, so you have about 30% of the capacity reduction. So you have alpha c value is equal to 0.715. That is coming from table number 6.3.3c. because your KF value is 1, your lambda n value is 74.4, alpha b value equal to 0. Now once you find this alpha c, you have this member axial capacity, member axial capacity, alpha c times ns. Alpha c was penalty. The standards apply the penalty for using the long columns. He said 30% capacity is gone, boom, is in the air because you have a long column. because you have stability. And NS we calculated 1998. So you have 1998 kilonewtons. Multiplications give you 1998 times 7.3. You have about 1425 kilonewtons. And if you just want to calculate with the reduction factors, and these 10% again more penalty, saying that you will be reduced because of this certainty. So you might forget to apply something, boundary conditions are in the real world. You will not have pin columns. There might be some kind of uncertainties that applied there. So that's the quick overview on that one. Let me know if you have any questions. We have almost 4 minutes, and I will get back.